Today I'm going to introduce DPC++ MapReduce on FPGA. We're going to implement a word counting using DPC++ on FPGA. Here's the word count problem. Given 4 keywords, that, with, have, and from, let's count their occurrences in a text file. If we use MapReduce, we can follow the MapReduce paradigm to first partition a large text file into multiple work groups. In this process, we use mapping processors to count the number of times each word appears in a text. And on these mapping processors, we produce key value pairs, where the word is the key, count is the value, and this count is locally obtained on this map processor. In the next stage, the reduction processors will receive the key value pairs from the mapping processors. So in this case, for example, R0 receive all the counters with the key V. So the reduction processors will receive the key value pairs and sum the word counts for each word and merge the results into their final listing. Within each of the mapping processor, we can compare the text with keywords. Here we have an example brute force search for 4 keywords. This stream is the text, this character stream is from the text file. So we have that book is from. And since we have 4 keywords, ideally we can compare the 4 keywords with each of the characters in the text stream. So it works in a sliding window fashion. So first we compare the beginning of the 4 characters from the text with all 4 keywords. And as we can see, we have a match here. And next step, we're going to move this window to the next character. At this point, the characters in the text stream does not have any matches. So we'll produce a no match and move on to the next location. So we basically slide the window by 1 character ahead. We'll continue this process to compare all the characters in the text stream with all the 4 keywords. And when we get to this point, we can find that there's another match with the keyword from. So from this example, you can see that while the mapping processors try to compare with each of the keywords, we have a parallelism here in that we can compare the text with the 4 keywords at the same time, if given abundant resource to do that. Before we start in the implementation of MapReduce for FPGA, we want to point out there are a few variations. First, the data partition is to be done by the CPU on the host. The CPU on the host will partition the whole text file into smaller chunks and assign them to devices. In the mapping stage, the data chunks will be mapped to work groups, which do the counting of keywords. And they will not produce key value pairs. Instead, they will do local reduce because the key value pairs will incur a lot of memory accesses. And because the computing resources on FPGA are all local, there's no need to send the key value pairs to other locations. So what we're going to do is the local reduce, which will retrieve chunks of data assigned, and then we're going to exploit the parallelism within data chunk and perform comparisons, like we just explained earlier. And after the counting is done, we will do local reduction to partially accumulate the counters to the global counters. And if necessary, we might need to do a global reduction for some other problems, but for our case, it's not necessary. It's optional. Here we want to use this diagram to explain what we just outlined. So the original text file will be partitioned into small pieces and assigned to these individual work items. This M0 is a work group 0, which has 2 work items, and these will be instances of the kernel that will work on the data partitions assigned to this work item. We maintain the counters in local memory so that these work items can access the local counters and increment them if it finds a match. And after that, these local results in local memory will be further accumulated to a global counter residing in global memory. Now let's look at what we have for the resources on the device. On the device, we typically have hardware resources for computing and for storage. For computing resources, we organize them using work groups and work items. Depends on how many physical hardware resources you have, you may be able to instantiate or execute multiple work groups. And within each work group, you have work items that can be individually executed in parallel. And for the storage resources, we have a few kinds of memory components: global memory, constant memory, local memory, and private memory. Global memory is the largest in capacity, but the access speed is slow. It is shared by all the work groups. Constant memory is a portion of it, which is used for read-only data. Within each work group, we have local memory, and this local memory is faster than global memory, but smaller in size. And local memory is shared by all the work items in that work group. Local memory is not shared by other work items across the work groups. Within each work item, it has its own private memory, which is the fastest, but the smallest in size. So in our design, we need to think about how we can program the resources so that we can utilize local memory, private memory more efficiently, because they are much faster than global memory. In this word counting example, we actually use local memory to store counters, which will be incremented by the work items in a work group. For FPGAs, we will define the work group size. Work group size is the number of work items in a work group. On FPGAs, typically we have one compute unit, because the memory controller could easily be a bottleneck if we have multiple compute units that's designed without any coordination. Because we have one compute unit, so we only need to have one work group, which will be mapped to the computer unit. And then within the work group, we can specify the work group size, that is the number of work items in the work group. And we use this parallel 4 kernel as an example to show you how we can define that. First of all, this parallel 4 is a reduction kernel, as we specify the class name as a reduction kernel. And it takes 2 arguments. The first one is the ND range, and that goes from a global size and local size. The global size is the total number of work items that we want to use to solve the problem. And then work group size is the number of work items within the group that we want to use. And then second argument to this parallel 4 is the lambda function. The lambda function will take the item as a argument, and this item is in fact an iteration of this ND range. So the item that we will use later in the lambda function will be able to represent different work groups and different work items while we iterate through all the work items. And before we define the actual operations in the lambda function, we use 2 macro definitions to specify the work group size. One is the required work group size, which takes 3 arguments, and these represent the 3 dimensions. Since we only use 1 dimension, so we only need to specify the very last one. That's the first dimension, which is the max work group size. And this could be a constant number that you define earlier in your program. could be 16 or 32, etc. And the second line is Intel specific non-SIMD work items. You can use the same macro definition to specify the size of the work group. In this way, the compiler will know that it will need to replicate resource for these many times to create computing resources for each of the work items within the work group. For each of the work group, in order to finish the word counting, it will do a few things. First, it needs to initialize local memory, which will be used to store the counters locally. And then it will need to load characters from the text file to determine whether one or more of the keywords are matched. This work item does not produce a key value key, however. If it does, it needs to report every match on the reduction stage, and it will generate a lot of key value pairs that will be stored in memory, and then the memory will become a bottleneck. Instead, this work item will increment the counter in the local memory corresponding to the matching word. So in this way, it does both mapping and local reduction. And one last step is when the local reduction is complete, and one of the work items in the work group will add the local results to the global results, which means that we also maintain the global counters in global memory, and each of the work groups and work items will need to increment the locally reduction result to the global result. There are still several remaining issues that we need to resolve. First of all, how to initialize local memory, and how to synchronize work items, because the work items will be started in parallel and their execution pace is undeterministic. So what if work items start counting the words before the counters in the local memory are initialized? And what if two or more work items attempt to increment the same counter? Because when they increment the counter, they have to perform read, add, and write operations, which have to be accomplished all at once without interruption. And finally, how to synchronize the final reduction stage. By that, we mean if the final reduction stage starts before all the work items finish their counting, we are actually adding incorrect local results to the global results. So we have to resolve that issue. First, here's how we allocate local memory. We can use accessors to declare an accessor to local memory. In this case, we define the type of the data is going to be unsigned int, and it's going to be one-dimensional. And the access mode is read and write, and the target, as we see here, we define the local. So this will be allocated in local memory. And the name of the variable followed by the range. We have one dimension, and we're going to allocate for these many keywords. And then finally, this is the handler from the lambda function. So in this way, we can maintain a set of keyword counters for all the work items in the work group. The next step is to initialize local memory. We need to initialize the local counters before work items can use them. And to do that, we pick one of the work items using this local ID. This local ID is the ID of the current work item. And we will just put in zeros to these local memory, which we used for the counters. The next, we use a barrier function. And this barrier function is very interesting. It will actually make sure that all the work items will wait here until everybody reaches this point. Because when everybody reaches this point, that means the local ID 0 will also reach this point. So these four counters are initialized already by that point. So barrier function is to support a read-write fence. The main purpose is to ensure that all the memory accesses preceding the barrier are executed before any work items can continue executing. So this is what we actually used in the previous slide. We set the barrier and using this definition to say this is a local barrier. We can change local barrier to global or global and local. In the diagram on the right illustrate what will happen when we have a barrier. So within this work group, we have 8 work items, which are started at the same time. They execute in parallel, and they proceed at different pace. And because of this barrier, and everybody gonna be waiting here until every one of the work items reaches to this point. And that's why we can make sure that the local counters are initialized before everyone can proceed to the actual counting. And this barrier can only apply to the work items within the same work group. So that's why you see these barriers are different from work groups to work groups. And there's no way to synchronize them across work groups. Next thing is about atomic operations. First, we want to talk about race condition. Race condition happens when multiple work items try to access the same or shared variable, and they have different outcomes if the access order is different. This typically happens when the access contains several steps. In our case, the counters, if you want to increment, you need to read the counters, update it, and then write the counter back. So these 3 steps have to be accomplished all at once without interruption. Atomic operations guarantee that not only a write operation occurs, but also that a read and write combined with some operations on the data occur without interruption. So an atomic operation either occur successfully or do not occur at all. That means they have no impact. In DPC++, we will define a local atomic reference in such way so that we can use this local atomic reference to specify what will be the operations that should happen atomically on a variable. So more specifically, for this local atomic reference, we define memory order to be relaxed, and the scope is within the work group, and the address space is local space. So in this way, this variable 1, which is a variable in local memory, will be incremented atomically. For variables in global memory, we can define similar references so that we can apply atomic operations on these global variables. So let's take a look at what we have in the lambda function for our work item. So first of all, we need to find the chunk of data for the current work item using the work group ID and work item ID. So this group ID and local ID represents the work group ID and work item ID respectively. And the first part of it is to define how many iterations we need to go through all the problem, since we may have a lot more data than the number of work groups and work items, and also the characters processed by a work item. So we're going to go through several steps. And within each step, these will be that many characters be processed. And for the current step, we need to figure out what is the current group ID. In our case, it's actually simple because we only have one group, so this is always 0. And the local ID is the ID of the work item. And then we have this for loop that we use to go through the every character in the chunk assigned to this work item. This offset comes from the computation, which we use to specify where do I start in the whole text file for this work item. And I'm going to go through these many characters for this work item. And then we will do some boundary checking to ignore the trading characters That's after the very last chunk. And the next two lines are to load a 4-character word, because all the keywords we want to compare 4-character words, and so we're going to load 4-character words from the assigned data chunk in the text file, and we use this text word .load, supply the starting pointer of the text data, and then plus this offset. And then the next for loop is to compare the loaded text word with all the 4 keywords. And note here we use X, Y, Z, and W to specify the individual elements in this 4-character vector. And in hardware, this comparison can be done very efficiently on FPGA, because we can have multiple comparator instantiated and to compare with the 4 keywords at the same time. If there's a match, we will increment the corresponding counter in the local memory. And note here that this is atomic increment, so we make sure that the read, update, and write operations are all completed at once without interruption. So all the work items will go through their data chunks and do the comparison with the keywords and update the local counters if necessary. And after that, we have another barrier. This barrier will make sure that every work item will finish before it moves on to the next local reduction phase. And the local reduction phase will just use one of the work items, work item 0, to accumulate the results from the local counter to the global counters. And note here we're using similarly a atomic operation on the variables in global memory. And we accumulate with the corresponding counters we counted in the local memory by the work items. So next we'll see a demo of the word count example on Intel Dev Cloud.